the accuracy of the result. Third, robustness. Arithmetic operations can also lead to numerical instability and divergence, especially when dealing with large or small values. By minimizing the number of operations, we can reduce the risk of numerical instability and make the algorithm more robust. Memory usage. Each arithmetic operation requires storage space in memory. By minimizing the number of operations, we can reduce the memory usage and optimize the use of available resources. Overall, minimizing the number of arithmetic operations can lead to more efficient, accurate, and robust algorithm with more memory requirement. Here, second question, avoid taking the difference of two nearly equal numbers whenever possible by alternate formulation of problem. If it cannot be avoided, then take the difference between doing other operations. Answer is true. Taking the difference of two nearly equal numbers can lead to loss of accuracy and numerical instability, especially when dealing with floating point arithmetic. This is because the difference between two nearly equal numbers can result in a very small number that may be lost due to the limited precision of floating point arithmetic. For example, consider the subtraction of two nearly equal numbers. A equals to 1.000000001, B equals to 1.0000002, C equals to B, A minus B. In this case, the value of C is very small and may be lost due to the limited precision of floating point arithmetic. This can lead to inaccurate result and numeric instability, especially if C is used in subsequent calculations. To avoid this problem, it is recommended to use an alternative formulation of the problem that avoid taking the difference of two nearly equal numbers. This can involve algebraic manipulation or recording of the calculation to reduce the sensitivity to small change in the input. If it is not possible to avoid taking the difference of two nearly equal numbers, it is recommended to take the difference before performing other operations. This can help to reduce the impact of the loss of precision and improving the accuracy of the result. Overall, avoiding the difference of two nearly equal numbers and taking the difference before performing other operations can lead to improve the accuracy and numerical stability of algorithms that involve floating point arithmetic. Question third, adding or subtracting numbers starting with the smallest number and works with number in ascending order. The answer is true. Explanation, adding or subtracting number starting with the smallest number and working with numbers in ascending order can lead to improve the accuracy and numerical stability of the calculation. When adding or subtracting number with different magnitudes, it is important to start with the smallest number to reduce the impact of the limited precision of floating point arithmetic. This is because small numbers have fewer digits and are less sensitive to rounding errors than large numbers. By working with numbers in ascending order, we can also reduce the accumulation of rounding errors and numerical instability. This is because rounding error accumulate more rapidly when adding or subtracting large numbers, while small numbers are less sensitive to the error. Question number 5. IL conditioning of problems is normally due to improper formulation and can be eliminated by carefully reformatting the problem. A practical way, if detect su- sub- suspected ill conditioning, is to alter the parameters by small amount and observe their efforts on the solution. The answer is true. Explanation. The statement is partly true. IL condition of problems can be due to improper formulation, but it can also be due to the nature of problem itself. IL conditioning means that small change in the input or parameters of the problem can lead to large change in the output or solution. This makes the problem difficult to solve accurately and can lead to numerical instability. One way to detect suspected ill conditioning is indeed to alter the parameters by small amount and observe their efforts on the solution. This is known as sensitivity analysis. By analyzing the sensitivity of the solution to change in the input parameters, we can determine whether the problem is well conditioned or ill conditioned. If the solution is highly sensitive to small change in this input, then the problem is likely to be ill conditioned. However, simply altering the parameters by small amount may not always be enough to eliminate ill condition. In some cases, a careful reformulation of the problem may be necessary to improve its condition. This may involve changing the formulation of the problem, introducing additional constraints or assumptions, or using a different numerical method of algorithm. Question 6. After a numerical algorithm is obtained, check if it can lead to numerical instability. In such algorithm, error grow in each step of the calculation. In such cases, reformulate the solution procedure to get a stable numerical algorithm. The answer is true. Explanation. The statement is partially true. Numerical algorithm can indeed lead to a numerical instability when error grows in each step of the calculation. This can be due to a variety of factors such as L-condition problem, numerical round of error, or instability in the algorithm itself. To ensure numerical stability, it is important to carefully analyze the algorithm and its implementation to identify potential source of instability. This may involve testing the algorithm on a range of input values, examining the behavior of the algorithm as the input value are varied, and comparing the result with analytical or extract solution where possible. If numerical instability is detected, then the solution procedure may need to be reformulated to get a stable numerical algorithm. This may involve using alternative numerical method or algorithm that are known to be the most stable. Modify the existing algorithm to reduce the impact of numerical error or roundoff. Therefore, while checking for numerical instability is an important step in the development of numerical algorithms, addressing instability may require more thorough analysis and reformulation of the algorithm to ensure that it is stable and reliable for a range of input values and conditions. Question 7. If severe rounding error and consequent loss of significant digit is anticipated, and if no alternative formulation to avoid this is problem, then carry more significant digit in the critical calculations using formulate floating point numbers in double precision mode. In this mode, the length of the mantissa is twice that of the other floating point quantities. The statement is true. Severe rounding errors and consequent loss of significant digit can occur in numerical calculation, particularly when dealing with quantities that vary widely in magnitude or when performing while operations on values that are close to the limit of machine precision. In such cases, if no alternative formulation is possible to avoid this loss of precision, carry more significant digit in critical calculation can help to minimize the impact of rounding error. One way to achieve this is by using floating point numbers. खुशी मत कर यार, तू पता मैं तेरी वीडियो बनाती हूँ, मैं कभी नहीं बीच में बोलती, नहीं मेरे से मत बात कर. वन वे टू अचीव दिस. रुक जा 2 मिनट. लास्ट क्वेश्चन, मेरे लास्ट के 2 क्वेश्चन बाकी हैं. अब सर इतना पार्ट आप काट देना है ना, मैं कंटिन्यू ही रख रही हूँ. One way to achieve this is by using floating point number in double precision mode, which allow for twice the number of digits in the mantissa compared to standard floating point numbers. This can help to increase the precision of critical calculation and reduce the potential for rounding error to affect the accuracy of the final result. However, it is important to note that increasing the precision of calculations can also lead to computational cost and memory requirement of the algorithm. Question 8. Double precision requires large memory space and slow down calculations. The statement is partially true. Double precision requires more memory space, the standard single precision, as each double precision floating point number requires 64 bits of memory compared to 34 bits for a single precision number. However, whether or not double precision slows down calculations depend on the specific context and computational requirement of the algorithm. In some cases, double precision may be necessary to achieve a desired level of accuracy or to avoid numerical instability caused by rounding error. In this situation, the benefit of increased precision may outweigh the additional memory requirement and computational cost. In other case, where lower precision is sufficient or where the computational resource available are limited. It may be more efficient to use single precision floating point number or to consider alternative method of formulation that reduce the impact of rounding error of the final result. Question 9. Question 9. In third iteration of finding square root of 5 with starting point 7 using Newton-Raphson method, relative error is 0.0013. The answer is true. To answer the question, we need more information such as the formula and the previous approximation opted. However, based on the given information, we can make more guesses. Assuring that the formula used to find the square root of 5 is x bracket n plus 1 equals to 0.5 bracket xn plus 5 upon xn, where xn is the nth approximation and x bracket n plus 1 is the n plus 1th approximation. We can estimate the value of x3 third iteration as follows. x x0 equals to 7 given starting point, x1 equals to 0.5 bracket 7 plus 5 by 7 equals to 3.07143, x2 equals to 0.5 bracket 3.07143 plus 5 by 3.07143 equals to 2.23862. Now assuring that the relative error is defined. Therefore, after solving all these equations, therefore, the third approximation of the square root of 5 using the Newton-Raphson method with a starting point of 7 and relative error of 0.0013 is approximately 2.24119. Question 10. The iterative method are compared on following parameters. First, the rate of convergence. Second, the amount of computational effort per iteration. And the third, sensitivity of the method to the starting value and the intermediate value. The answer is yes, correct. Two, the iterative method are commonly compared based on the following parameters. The correct answer is A, the rate of convergence. It refers to how quickly the iterative method converges to the desired solution. The faster the rate of convergence, the better the method. B, amount of computational effort per iteration. It refers to the amount of computational required to obtain the next approximation in the iterative process. A method that requires less computational effort per iteration is preferred. And the C, sensitivity of the method to the starting value and the intermediate value. This refers to how sensitive the method is to the initial guess and intermediate value used in the iterative process. A method that is less sensitive to the initial guess and intermediate. Thank you.